These are the frequently asked questions for pre-calculus from section 1.5, day 2, starting with number 15. It says in exercises 13 to 22, find a formula for the inverse of x and give the domain of that inverse, including any restrictions that are inherited from f. So as I start number 15, I'm looking right away to see those restrictions. And so what you would do is you would say, all right, well, first of all, I know there's going to be a vertical asymptote at x equals -1. So I can't use -1. It would make it a 0 in the denominator. So the domain of f has to leave out that -1. So negative infinity to -1, hop over, and go from -1 to infinity. So if I can't use a -1 at that point, then this becomes about, what's happening with the range. What is that doing to this function? And so what you would do is graph it and take a peek and figure out just exactly what is that doing to the range of this function by taking 2x minus 3 and dividing that by x plus 1 if we cannot include the -1. And the graph that we get from this function shows us a horizontal asymptote, which again we can do algebraically, but I just wanted to give you a visual without having to pull up that smartboard calculator that takes so much time and memory from a calculator. So we do see it looks like there's going to be a horizontal asymptote, and we realize that where that's coming from is if we had infinity and infinity, it's going to be 2 over 1. So we would have a horizontal asymptote at y equals 2. And if that's the case, then that means our domain, our range, is never going to get to that 2. So negative infinity to 2 in union with 2 to infinity would be our range of f. So now let's go after the actual inverse of this function. And that means we start with y equals 2x minus 3 over x plus 1. And then what we do is we go ahead and switch the x and the y and solve for y. I'm going to have to do some small writing here because the smartboard has decided to misbehave again. So let me erase this and start with this. So what we have to do is switch the x and the y and then solve for y. So what we'll need to do is get that y plus 1 out of the denominator by multiplying both sides by y plus 1. So xy plus x equals 2y minus 3, because these two y plus 1 and y plus 1 would cancel out. Now let's get anything with a y in it on one side and everything else on the other side. So xy minus 2y equals negative x minus 3. Let's factor out a y. And now we can go ahead and divide both sides by x minus 2. So we would have our inverse, which equals negative x minus 3, and that is over x minus 2. So now we need our restrictions. And again, what we can do is we can think about our domain and our range are going to be flipping as we go through this inverse process. So for number 15, and again, there's a lot of different ways that we could write this, and that might have been what you noticed in the back of the book, but negative x minus 3 over x minus 2 will work just fine. We could go ahead and say, all right, this is a -1 times x plus 3, and just leave it like so, distribute it on the bottom, whatever you wanted to do here. There's a lot of different ways that we could write that, but this answer would be just fine. But what we do need to know is the range of the original now becomes the domain of the inverse. So the domain of f inverse is negative infinity to 2 in union with 2 to infinity. So a reminder, the domain and the range are going to switch positions. 24 and 25 say determine whether the function is 1 to 1. If it is 1 to 1, sketch the graph of the inverse. In order to be 1 to 1, it has to pass both the vertical line test and the horizontal line test. So for number 24, that's not going to pass the horizontal line test. So this is not 1 to 1. Not 1 to 1. Number 25, that one will pass the horizontal and the vertical line tests. So what we want to do is sketch the graph of the inverse. And to sketch the graph of the inverse, we have to remember that that's going to be the reflection over the line y equals x. So we can either pick a few points and reverse the x's and y's, or just try to do this visually and see if we can't get a decent match for the inverse. So again, you can pick points if you want to, but I don't think that's a bad representation there of the inverse, that reflection over the line y equals x. You could certainly do something like say, all right, well, this point originally was at 0, negative 2, so the inverse of the function would have that at negative 2, 0. And yeah, you see I was a little bit off there, could have gone out a little bit more. But either way, however you want to do it, you can get those points. Next one up was 31, confirming that these are inverses of each other by showing f of g of x and g of f of x. So for 31, if we take f of g of x, that means that we are going to take 1 over x minus 1, and wherever we see an x in f of x, we will replace it. So there are actually 2 spots we need to do that this time. So this will be 1 over x minus 1 plus 1 all over 1 over x minus 1. All right, so what we would want to do is get a common denominator. We would multiply this one. Actually, we could actually multiply everything in here by the least common denominator and get rid of all this stuff right away. So let's multiply everything on the top and everything in the bottom by x minus 1. Here the x minus 1's would cancel out and we would get 1. And this would be 1 times x minus 1. And on the bottom the x minus 1's would cancel out and we would just get 1. So now we see that we have really just 1 plus x minus 1, which is x. So that was f of g of x. That's probably the easiest way to go after that one. And then we do that backwards and find g of f of x. So this goes down here. And that would give us, we would have 1 over x plus 1 over x minus 1. All right, so again, we could get rid of this very quickly by just multiplying everything in the numerator and everything in the denominator by the LCD, which in this case is going to be an x. So when we do that, on the top, numerator will have an x. X's will cancel out here, and we'll get x plus 1. And then x times negative 1 will be minus x. And that will give us x over, well, x minus x, that's gone, which is x over 1, which is just x, which is exactly what we wanted to happen. That's how we show that they are true inverses, is by seeing, pardon me, that f of g of x and g of f of x both give us an x for an answer. And for 32, same thing. We've got a lot of places to put these fractions, so let's try f of x, f of g of x, and that will mean we're going to take this function and we're going to be putting it in 2 different places. So 2x plus 3 over x minus 1 plus 3 over, and then we'll have it down there again, so 2x plus 3 over x minus 1 minus 2. And again, this is probably the easiest thing to do by multiplying by that LCD of x minus 1. Here the x minus 1's will cancel out, and we will get 2x plus 3, and then the 3 times x minus 1. Pardon me. And then our denominator, these x minus 1's will cancel out, and we'll get 2x plus 3 minus 2 times x minus 1. So this will give us 2x plus 3 plus 3x minus 3 over 2x plus 3 minus 2x plus 2. Well, 2x plus 3x is 5x. 3 and negative 3 are 0. 2x minus 2x is 0, and 3 plus 2 is 5. And 5x divided by 5 is x. Then we need g of f of x. All right, so other direction. We have to take f of x, and in the two spots that we see x, we're going to put that nice little fraction. So this will be 2 times x plus 3 over x minus 2 plus 3 all over x plus 3 over x minus 2 minus 1. Now, again, let's just go ahead and use that least common denominator here, which is x minus 2, and multiply everything in the numerator and the denominator by x minus 2. Here the x minus 2's will cancel out, and we will get 2 times x plus 3 plus 3 times x minus 2. In the denominator here, the x minus 2's will cancel out, and we will get x plus 3 minus 1 times x minus 2. So we will have 2x plus 6 plus 3x minus 6, pardon me, all over x plus 3 minus x plus 2. Well, our numerator is going to be 5x, because 6 and negative 6 will drop out. X minus x on the bottom, the x's are gone. And we have 3 plus 2, which is 5, and 5x divided by 5 is x. So those two, especially 31 and 32, easiest to solve by going ahead and multiplying everything in our complex fraction by that LCD. Number 33, we have some currency conversion taking place here. And this says that in May of 2002, the exchange rate for converting US dollars to euros was y equals 1.08x. And A says, how many euros could you get for 100 US dollars? Well, if this is the exchange rate and US dollars are x, then for part A, we're just going to go ahead and stick a 100 in there. And that will give us 108 euros. Part B, what is the inverse function and what conversion does it represent? So switch your x's and y's and then solve for y. Now, we might actually want to find that inverse of the 1.08 and see if that's something nice. And we would just punch in 1 divided by 1.08, and that would be approximately 0.926 for y, but we wouldn't have to. We could leave that, and it would be more exact if we leave it as it is. That's x over 1.08 equals y. Now, this would actually be what we would use to convert euros to dollars. Got the little x in that spot right there. Hang on 1 second. 0.926x equals y. Convert euros to dollars. All right, part C. In the spring of 2002, a tourist had an elegant lunch in Provence, France, ordering from a fixed price €48 menu. How much was that in US dollars? Well, to tell you the truth, I would probably go back to the beginning here. Because again, this was rounded. And we want to know 48 euros is what in US dollars? So we would multiply both sides by, divide both sides by 1.08. So 48 divided by 1.08 comes out to $44.44. Since this is dollars and cents, we would not go 3 decimal places on this. You always want to think, what is the problem really about? And since it's about money, $44.44 is what we're going to want. And the smartboard is still being an issue here today. So you're going to hear a pause every once in a while I try to figure out how to get the smartboard to behave itself. All right, now 35 and 36. Which pairs of our basic functions are inverses of each other? Okay, so first thing I want to do is think to myself, all right, if it's an inverse of each other, it should be undoing something else. And so as I look at these functions and I think y equals x, well, it's its own inverse. You know, that's going to be an answer to number 36. Because if you reflect the line y equals x over the line y equals x, it doesn't go anywhere. So I start looking for things like the cubing function, which is y equals x cubed, and its inverse would be the cubed root. And that's not one of our 12 basic functions, so there's no point in that. And I start thinking right away, well, what about y equals x squared? Its inverse is definitely one of the 12 basic functions, and that's our square root function. So which pairs are going to be inverses of each other? Right there. The squaring function and the square root function. And then one more pair that you're probably not real comfortable with, and that is y equals e to the x and y equals the natural log of x, because natural logarithm is how we undo that base e. Now, remember that if we are going to talk about y equals x squared and y equals the square root of x, there is an issue, and that issue is about the domain. When you look at this picture, you realize that we are definitely restricting that domain. So this one would count if we restrict the domain. And that's number 35. So y equals x squared and y equals the square root of x would be inverses, but only on the domain from 0 to infinity. As we talked about in class, sometimes you have to restrict those domains to get things to work. Y equals e to the x and y equals the natural log of x. Those are inverses of each other. There's no restrictions on the domain for that. And then for 36, y equals x. Remember I had talked about earlier being its own inverse, but that's not the only one. So what we have to do is think, okay, which one of these would we, if we drew in our line y equals x, would we get the exact same thing that we get right now? And that was one of the things that we had talked about when we went through these 12 basic functions, that the reciprocal function is its own inverse. That actually was in your notes how we discovered that y equals 1 over x, or f of x equals 1 over x, was its own inverse. It is 1 to 1. And then, of course, y equals x, because it is on the line y equals x, so it's not going to go anywhere if we reflect it. It is its own inverse. Number 41. Which ordered pair is in the inverse of the relation x squared y plus 5y equals 9? So let's switch the x and the y, and let's solve for y. So y squared x would equal negative 5x plus 9, and then we would divide by x, so y squared equals negative 5x plus 9 divided by x, and then we take the square root and get plus or minus the square root of negative 5x plus 9 over x. And then what we want to do is just see which of those points is actually going to work in number 41. So it basically becomes a trial and error problem as you go through there. So if we put a 2 and a 1 in here and give it a try, 2 times -5, that would give us -10. -10 plus 9 would give us -1 over 2, and we're saying the square root of that is going to get us a 1. Not going to happen. So 2, 1 is out. -2, 1. Well, -5 times -2 is 10. 10 plus 9 is 19. Square root of 19 over -2. Can't even do that. That's imaginary. Then we go to -1, 2. -5 times -1 is 5. 5 plus 9 is 14. And all of that, that would be a -14, and that's imaginary. Then we have 2, -1. -5 times 2 would be -10. -10 plus 9 would be -1. -1 divided by 2. Sorry, not going to happen. All right, one more to go. 1, -2. -5 times 1 is going to give us -5. -5 plus 9 is 4 over 1. And the square root of 4 over 1 is positive and -2. Boom, we found it. That's going to work. So, as often is the case when you have a trial and error problem like this, the very last one was the one that worked in the problem. And that is it for this section.